Using the asymptotic distribution or the approximate distribution for the OLS estimator, we can do something new actually, something that we had not been doing before the midterm. That is testing multiple hypotheses. Now with this approximate distribution for this random vector beta hat minus beta, we can test a multiple hypothesis that looks like this. So what is a multiple hypothesis? A multiple hypothesis is a hypothesis that asserts more than one equation, that is defined by more than one equations. For example, this one is defined by two equations, beta 1 equals 0 and beta 2 equals 0. So even though I wrote it as one equation in terms of a two-dimensional vector, that effectively means two equations, beta 1 equals 0 and beta 2 equals 0. And this is an example of a multiple hypothesis. How do you test a multiple hypothesis? Before talking about that, let's consider an example where testing multiple hypotheses is relevant. In this example, suppose that Y is hourly earning, and consider also two measures of physical features, height, age, and BMI. Also suppose that the conditional mean of Y given age and BMI is described by this equation. Now, if beta 1 and beta 2 are not 0, then that means expected earning varies with physical features, varies with height or BMI or both. Now, we do not know whether hourly earning varies with height or BMI or not. We would like to know whether it does. So to do that, we can let the null hypothesis be people with different height or BMI do not have different expected earnings. This verbal statement can be described by a multiple hypothesis about beta 1 and beta 2. That's beta 1 equals 0 and beta 2 equals 0. When we reject the null hypothesis, that means we have evidence for that expected Y does vary with some physical features. Now, to figure out how to construct a test for multiple hypotheses, let's consider this generic form of a multiple hypothesis for the regression equation. This generic form is written in terms of a linear equation system about beta, about the true parameter value beta. In this linear equation system, we got a known non-random matrix A, which is M by K plus 1. And we also got a known non-random vector B, which is M by 1. And then in this case, this multiple hypothesis is M-dimensional. It contains M equations. These M equations are also called M restrictions. So how do we test these M restrictions? For this general notation covers the special case that beta 1, beta 2 equals 0 in the following way. Let's suppose that the beta vector is composed of the intercept beta 0, beta 1, and beta 2, the slope coefficient beta 1, slope coefficient beta 2. So the whole vector of the regression coefficient is this 3 by 1 vector, beta 0, beta 1, beta 2. And now the null hypothesis is only about the second and the third. So how do we pick the second and the third from this whole vector? We pick it using an A matrix that's of this form. That's first row of A is 0, 1, 0, which when you multiply it to this whole vector of betas, it picks out beta 1. And the second row is 0, 0, 1. When you multiply that to this vector, you pick out beta 2. So therefore, if you let A to contain these two rows, then it picks out big beta 1 and beta 2. So this null hypothesis written in the generic form will need an A that is this and B that is 0. So this can be written in the generic form with A equals 0, 1, 0, 1, 0, 0, 1, and B equals 0, 0. How do you then test these multiple hypotheses? In order to introduce the basic idea of the test, we would like to consider a simple scenario. For this simple scenario, you can actually forget about the whole variance covariance estimation stuff for the OLS estimator. You can forget about OLS estimator actually. Just take this beta 1 hat and beta 2 hat to be some estimator for beta 1 and beta 2. And suppose in a simple setting, just for now, beta 1 hat and beta 2 hat minus beta 1, beta 2 follows this normal distribution exactly. What does it mean? So this means beta 1 hat has variance sigma 1 squared divided by n. Beta 2 hat has variance sigma 2 squared divided by n. And there is no correlation between beta 1 hat and beta 2 hat. Suppose this sigma 1 squared and sigma 2 squared are known. Then how do you test these multiple hypotheses? The first step to test this null hypothesis is to measure the discrepancy of the data to the null hypothesis. That is, how much evidence there is in the data against the null hypothesis. Well, in the data, the information about beta 1 and beta 2 will be contained in the estimators, beta 1 hat and beta 2 hat. If these are far from 0, then that would be evidence for H naught doesn't hold. So therefore, a natural measure of the discrepancy of the data to H naught will be the difference between beta hat, beta 1 hat, beta 2 hat, and the hypothetical value for the betas. That's the 0. So this is a natural measure of discrepancy. But this cannot be used as a test statistic because it's two-dimensional. It's not a number. So we will need to aggregate up these two dimensions, these two elements of the vector. How do we aggregate them up to form one scalar test statistic? Our proposed scalar aggregation, will be the weighted sum of the squares, where the weight is given by the inverse of the variance of each element. So it's easy to understand why we want to square it, because both positive and negative deviations from 0 is considered deviation. So they should be treated the same. So squaring will treat both positive and negative deviations as deviations. But then why do you want to use the inverse variance, the inverse of the variance of the estimator as the weight? The reason for using the inverse of the variance as the weight is twofold. There's one intuitive reason, that is the following. An estimator with high variance is less accurate and therefore less informative about the null hypothesis. If it is less accurate and less informative, then in our testing, we should take it less seriously. In weighting the component, weighting this component by the inverse of its variance is the way to mathematically take the higher variance component less seriously, because higher variance means smaller weight for that component. So that's the mathematical way to give a more variable estimator less weight. And there actually is a more practical reason. The second reason is the more practical reason. The practical reason is the following. When you divide beta 1 hat by its standard deviation, you're going to get a standard normal random variable. And same thing for beta 2 hat. That is, once you use the standard deviation to weight, the inverse of the standard deviation to weight each of the two elements of beta hat, beta 1 hat and beta 2 hat, you obtain a random vector that follows the standard normal distribution that has two elements that are independent standard normals. And Wn is the square, is the sum of the square of the two. Therefore, it has the same distribution as the sum of the square of two independent standard normal random variables. Sum of two standard normal random variables follow a simple distribution that's called the chi-squared distribution. That is a very well-known distribution. Therefore, just by using the inverse variance weighting, we obtain a test statistic that follows a simple distribution chi-square 2 under the null hypothesis. And from our discussion of hypothesis testing before, having a simple distribution under the null hypothesis is important. It's very useful because we need to take the critical value for the test from that simple distribution, from the distribution of the test statistic under the null hypothesis. So if that distribution is simple, then it's easy to come up with that critical value. So therefore, that's why we use inverse variance weighting. And from that null distribution, chi-square 2, we can take the critical value chi-square alpha 2, which is the 1 minus alpha quantile of the chi-square 2 distribution. And we let our test be to reject H naught if Wn is greater than chi-square critical value, okay, chi-square alpha 2. And that test has good rejection rate because probability of rejection when the null is true is the probability that Wn being greater than chi-square critical value given H naught. And given H naught, the distribution of Wn is chi-square 2 just by construction, as we explained on the previous two slides. So therefore, that by the definition of this quantile, that is alpha. So therefore, the null rejection probability is exactly alpha, and that is good. That means we exactly control the null rejection probability or the probability of type 1 error. So that is the intuitive reason for why we use inverse variance weighting in a simple example. In more complicated examples, it's basically the same idea. And let's now go to the more general case. In the more general case, we are testing this null hypothesis, and we want to base the test on an estimator for beta, estimator beta hat for beta. To construct the test, the first step is to evaluate the discrepancy between H naught and the data. That is, how much evidence there is in the data against this equality. Well, that natural measure would be obtained by plugging beta hat in for beta and see how different from zero these two sides of the equation is. So that is, you take A beta hat minus B and see how different from zero this is. But of course, this is an m-dimensional vector. We need to aggregate the elements in the vector up into a test statistic. And the way of aggregation is to use inverse variance weighting. That is, we take the quadratic form of this random vector with a weight, and that weight is supposed to be the inverse of the approximate variance covariance matrix for A beta hat. So what is the approximate variance covariance matrix for A beta hat? Well, we know the approximate variance covariance for beta hat is V hat divided by N. Then that for A beta hat should be A times that times A transpose. So therefore, it should be this. That's the approximate variance covariance matrix for A beta hat minus A beta. Therefore, we use the weight that is the inverse of that matrix. And using that, we construct the statistic that is this form, that is of this form. And that is, in general, we call that the Wald statistic. The Wald statistic, we are going to state without proof. The proof is kind of tedious and it's not required. We state without proof that under the null hypothesis, Wn is approximately chi-square m distributed. And chi-square m is the distribution of the sum of the square of m independent standard normal random variables. Then clearly, because this is the approximate null distribution of the test statistic, we can use the 1 minus alpha quantile from this distribution as the critical value. And that is denoted the chi-square critical value, chi-square alpha m. We reject the null hypothesis if Wn is greater than this chi-square m critical value. So that is the general form for the multiple hypothesis test. For historical reasons, people in fact refer to this as the large sample F test because people often use Wn divided by m and call that Fn, and that is the F statistic, the large sample F statistic. And if you use that as the test statistic, then the critical value should also be divided by m. That would be the large sample F critical value. So calling it F test or chi-square test is the same thing, and it's exactly the same test because it's the same rejection rule. But we're going to refer to it by the large sample F test. For any test, you can calculate the p-value, and for F, and that's the case for the large sample F test as well. To calculate the p-value, you know what the p-value is. The p-value is the probability that a randomly generated data set will contain stronger evidence than your current data set, according to your statistic, your test statistic. To compute the p-value, we first need to obtain the realized value for Fn, and we denote that by little fn. That's the value for the test statistic Fn computed using your given sample. That's the realized value for Fn. And what is the null distribution for Fn? That's chi-square m divided by m. So the p-value will be probability that the null distribution greater than the realized value for that statistic. If the p-value is small, that means the data contains strong evidence against the null hypothesis. And if the p-value is large, then it doesn't. Now, let's consider several examples of multiple hypothesis testing in the regression context. The first example is the overall significance test. What is the overall significance test? To know what that is, let's write a conditional mean model in terms of this form. What is this form? This form simply separate the intercept from the slope coefficients. We write the intercept out and write the part with non-constant x variables here. So this x1 vector, it doesn't contain the constant coordinate. So that equals x1 to xk. And that beta vector, beta 1 vector equals beta 1, beta k. Now, there is this null hypothesis that beta 1 vector equals 0. And that under this null hypothesis, if this is true, if this is completely 0, that means y is mean independent of all the explanatory variables, meaning that the expected outcome does not vary with any of the explanatory variables. And the model is not explaining anything about how y varies. So testing this null hypothesis is like testing whether the model matters at all. And the large sample F test for this null hypothesis is called the overall significance test of this model. And how do you do this test? Clearly, you want to figure out the A matrix corresponding to this. In fact, this A matrix should be 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So this A matrix can pick out the second to the k plus 1th element of the whole beta vector, and the B vector should be completely 0, this k by 1, 0 vector. So that's the overall significance test as a multiple hypothesis test. The second example of multiple hypothesis testing is to test the existence of group difference. Now, let's first consider a dummy that defines two groups. Say D is the dummy that defines two groups, say female group and male group. And let Z be other explanatory variables like schooling, weight, and BMI. Let Y be earning, an outcome variable or dependent variable. We want to know whether the conditional expectation of Y given Z for one group is the same as that for the other group or not. If that is what we want to know, then we would be testing whether these two coefficients are zero or not in this long regression, including D and the interaction term between D and Z. So why is that the case? That is the case because expected value of Y given Z G equals 1 equals beta 0 plus beta D plus beta Z vector plus beta ZD vector times Z. So that's the conditional expectation of Y given Z for the female group. We can figure out that same thing for the male group, and that will be beta 0 plus beta Z prime Z. In order for these two conditional mean functions to be exactly the same, you want beta D to be 0 and beta ZD to be 0. So therefore, testing group difference amounts to testing beta D, beta ZD equals 0. There are 1 plus DZ restrictions that we're testing. Now, the third example is testing for nonlinearity. Suppose in the true conditional mean model of Y given Z, Z is a random variable here, is beta 0 plus beta 1Z plus beta 2Z squared. And we don't know whether beta 2 equals 0 or not. If beta 2 equals 0, then we do not need to include this square term. If beta 2 is not 0, then we need to, because otherwise we're going to miss this nonlinearity and our conclusion will be misleading. So to test whether Z2 should be, Z square should be included or not, we can estimate this long regression and test beta 2, test whether beta 2 equals 0 or not. For this, actually we don't need an F test. We can do a two-sided t-test. Last example is to test for interaction. Consider the same conditional mean as in example 2. Z is a vector of covariates and D is the gender dummy or some other dummy, some other group dummy. And if beta 3 equals 0, if beta 3 equals 0, that means the gender difference of Y will be a constant beta 2. It doesn't vary with Z. But if beta 3 is not 0, then the gender group difference will be beta 2 plus beta 3 times Z, which will be a function of Z. Right? So in order to test whether the gender difference of Y varies with Z or not, one can test the null hypothesis that beta 3 equals 0. In this case, DZ number of equations, restrictions are tested. So you can figure out your A and your B in the general notation and construct the F statistic And you're going to use the chi-square dz divided by dz critical value for your large sample F test.